On to chapter 2, functions and their graphs. Let's start with section 2.1 on functions. In 2.2, we'll concentrate on graphs. And in the remainder of the chapter, we'll build up a library of functions and add to the library on occasion. We'll do that the rest of the course. One of the last things we'll add to the library are logarithmic and exponential functions. So we'll carry this library of functions idea from chapter 2 throughout the rest of the course. For now, 2.1, let's define functions to get a clean idea of what a function is. We'll, in this section, find the value of a function, find the difference quotient of a function. This is something you'll see again in Calculus 1. We'll find the domain of a function defined by an equation and form sums, differences, products, and quotients of two functions. We'll make new functions out of old functions through those operations. First, a definition of a relation. And we'll see that a function is a special kind of relation. A relation between two sets, x and y, is a set of ordered pairs of the elements of the two sets. We considered set notation and talked about sets in one of the appendices. I think it was Appendix A1. If element lowercase x is an element of set capital X, an element lowercase y is an element of set capital Y, and the ordered pair lowercase x, lowercase y is in the relation. Remember, the relation is a set of ordered pairs. So elements of the relation itself look like this. Then we say x corresponds to y, or y depends on x, and sometimes write, maybe I'll read this as maps to x, maps to y, or yeah, okay, x maps to y. There's a special symbol for maps to that's somewhat different from this, and it has a subtly different meaning, but verbally I got to call it something. X maps to y. Now, we've got this verbal awkwardness as well with whether I have a lowercase x or a capital X. Remember, the standard from Appendix A1 was to use the lowercase letters for elements of the set and the capital letters for the sets themselves. So that'll be the situation. And in this conversation of sets, a little of conversation of functions, a little bit of the set theory stuff is unavoidable. So a quick little made-up example to illustrate a relation. We could define a relation between the people in this class and the makes of cars we drive. One element of this relation would be Dr. Bob, Volkswagen. Another relation is probably X Volkswagen, where X is one of you. If so, then we say Dr. Bob corresponds to Volkswagen, and we say X corresponds to Volkswagen. That is, Dr. Bob is mapped to Volkswagen and X is mapped to Volkswagen. In this relation, we may have more than one element of X, for example, Dr. Bob and X, corresponding to the same element of Y, that is, corresponding to Volkswagen. So there may be one element of set capital X that or more than one element of capital X that corresponds to the same element of Y in a relation. Hey, sometimes I drive my wife's Toyota. So another element in the relation is Dr. Bob, Toyota. Dr. Bob is mapped to Toyota. So in a relation, one element of X can be associated with, correspond to, more than one element of Y. In this example, Dr. Bob corresponds to both Volkswagen and Toyota. These are properties, again, of a relation. Functions are a little bit different from that. Some additional observations are some elements of X may not correspond to anything in Y. There might be people that don't have a car. Also, some elements of Y may not depend on any element of X. None of us may drive a Mercedes, for example. In the definition of a function, we deal with a relation, but it's a relation with some extra properties. Let X and Y be two non-empty sets. This is a big moment in Precalculus 1. A function from X to Y is a relation, told you so, that associates with each element of X exactly one element of Y. The set X is the domain of the function. If lowercase x is in set X and lowercase y is in set Y, and X corresponds to Y in the function, that is, if you have the ordered pair X comma Y in the relation, then Y is the value of X. It's the value of the function at X. The range of the function is the set of all elements of Y which depend on elements of X. So we've defined here function, domain, value. I don't care much for the way they've dealt with that. We'll have some notation for it here shortly that's more familiar to you. And we've defined range. So in terms of a picture, and using arrows to represent the correspondences, we get something like this. The domain consists of these 3 points right here. They've labeled this one X. Here's the set Y. Set Y is not the range of the function. Set X is the domain. The range is the stuff over here that's images of things over there, the things over here which correspond to things over there. So the range consists of these 2 points because I look for, throughout set X, things that correspond to the elements of X. This corresponds to both these, and this corresponds to X. Sorry, corresponds to this point. So these 3 things in the domain correspond to these 2 things. Therefore, these 2 things form the range. These 2 points out here, there's no arrows going into them. They're not part of the range. The idea we had with the relation and the makes of cars. So I might have a Mercedes being one of these points here. None of us drives a Mercedes. It's not in the range of that little description we had above. Here we see 2 things mapped to the same thing over here. Point Y corresponds to both this point and this point in the domain. Nobody disallowed that. There was something that was disallowed. Says each element of X is associated with exactly one element of Y. So this element is associated with exactly that element. This element of the domain is associated exactly with that element. This element is associated exactly with that element. What's disallowed is maybe this element X being associated with both this and this. No, there's what the meaning of this in the graph is. There's exactly one arrow coming out of each of these. When I say exactly one, I mean there's one, not more than one, and not less than one. So each point over here in the domain has an arrow emanating from it. One arrow emanating from it. Over here in set Y, sometimes it's called a codomain. That's a term you'll hear in linear algebra, another one of our algebra classes. But what happens over here in set Y is some points have no arrows coming into them. Some points have one arrow coming into them. Some points have more than one arrow coming into them. So over here, kind of anything's possible. But over here in the domain, there's one arrow coming out of each of those elements of the domain. Our example is about cars as a relation. It's not a function. That's because the element of capital X, called Dr. Bob, corresponds to more than one element of Y. If we were to deal with that in a diagram like this, might have Dr. Bob here corresponding to Volkswagen and corresponding to Toyota. You can't have 2 arrows coming out in a function. In a relation, that's fine, but not in a function. Again, it's the exactly one comment here. Each element of the domain is associated with exactly one element of the set Y. The text says, the idea behind a function is its predictability. If the input is known, we can use the function to determine the output. If in non-functions, we don't have this predictability. This is how they state it on page 47. I would state it more concisely. This is my wording here, I think. For a function, no input has more than one output. And every input is a valid input from set X. It's where the function is defined. It's the domain of the function. Let's illustrate it with a couple of examples in line with the current conversation. Here's a relation represented graphically. State the domain and range of the relation pictured here. Determine whether the relation represents a function. I'm not so self-obsessed that I went and stuck my name in here. This is just example or exercise number 20 from this section. Got the same problem our previous relation had in terms of being a function. All right, they want the domain. Well, all these elements, Bob, John, and Chuck, have arrows emanating from them. So the domain is this whole set, father, as it's labeled. Since an arrow emanates from each of the listed fathers, Bob, John, and Chuck, yeah, then that's the domain. The range is daughter, since everything over here has an arrow coming into it. An arrow terminates at each of the listed daughters, Beth, Diane, Linda, and Marcia. So this makes up the range of the function. Now, I'm sorry, the range of the relation. Now, is this a function? We could have two arrows ending, terminating, at the same element of set Y, but we can't have two arrows coming out of the same element of set X when we have a function. That's that exactly one. I can't have this input associated with two outputs. This is a relation. It's not a function. A function associates with each element of the domain exactly one element of the range. But here we see Bob and the domain is associated with the two elements, Beth and Diane, in the range. So this is not a function. You can't have in these graphical representations of relations, you can't have two arrows coming out of the same thing in the domain. For a function. This is a relation, not a function. Let's look at another one, more in line with what we'll normally do. Consider the relation given there. Remember, a relation was a set of ordered pairs. So a function is a set of ordered pairs as well, if we really dissect it. We just had this graphical way of drawing things in the two little examples with the sets, with the X's and the Y's and the fathers and daughters sets. This is more like what we'll normally deal with. Still, we'll deal with something a little more general than this, but this is a little bit more in line. This idea of ordered pairs. Here's a relation. -2 is associated with 16. -1 is associated with 4, 0, and so forth. State the domain and range of this relation. Determine whether the relation represents a function. Well, if we look at X, Y, these ordered pairs in the relation, we say X corresponds to Y, X is mapped to Y if you like. So the domain, capital X, is a set of all first entries in the list of ordered pairs. So the domain consists of the first element, the first element, the first element, the first element. That's -2, -1, 0, 1. That's the domain of this relation. The range is the stuff that comes out of that relation. That'd be the second element in the ordered pair. So the range, Y, is a set of all second entries in the list of the ordered pair of correspondences. So we get 16, 4, 3, and 4. 16, well, 3, 4, and 16. Let's list them in order. You don't list 4 twice. 4 occurs twice. Don't list it twice. That's not how sets work. We went through that in Appendix A1. A set either contains something or doesn't contain something. It doesn't contain something more than one time. You wouldn't say the set consisting of 3, 4, 4 again, and 16. That's not how sets work. Either elements are in it or they ain't. 4 is in it. It's not in it twice. It doesn't work like that. That's not the way sets behave. So that takes care of domain and range. Does it represent a function? As long as we don't have the same thing in the first entry twice, and we don't, then we got a function. The function associates with each element of the domain exactly one element of the range. And that's the case. -2 is associated with exactly one thing. It's associated with 16. -1 is associated with exactly one thing. It's associated with 4. 0 is associated with exactly one thing. It's 3. 1 is associated with exactly one thing. It's 4. Each of these correspond to exactly one of these. Not to be confused by the fact that, hey, 4, -1 is associated with 4, and 1 is also associated with 4. Yeah, so -1 is associated only with 4. 1 is associated only with 4. In testing for a function, that's the way you look at it. Make sure each of these is associated with exactly one of these. Not one of these is associated with 2 of these. I can have 2 of these in the range be associated with 2 of the domain elements. 4 is associated with both -1 and 1. But I'm looking at the range there, and that's not how you deal with functions. A function had each element of the domain of this set here associated with exactly one element of the range, and that's the case. Even though the 4 is used twice as that thing associated with these, that's okay for just the function. Back to the notes. It's common to think of a function as a machine. You give it a good input, that is an element in the domain, and it gives you a single output, that is an element of the range. Like a calculator is one of these machines. You put a number in, you hit a function button, a trig function, square root function, log function, exponential function, any other kind of functions it might have built in, and it gives you an output or an error. If it gives you an error, you didn't put something in the domain in. You didn't give it a good input. You chose something not in the domain of the function. For example, you can't take square roots and negatives. So I couldn't hit the square root button to take the square root of -4, say. That's not in the domain of the square root function. Unless you have a sophisticated calculator and you've got it set to deal with complex numbers. So not for us, that's not a good number. So think of a function in this sense as a machine. You put good stuff in, you get a single output, This goes back to when we talked about square roots. Remember, square roots are never negative. The square root of 9 is +3. Put it in a calculator. Enter 9, hit the square root key. It gives you 3 out. It doesn't give you -3. Granted, -3 squared equals 9, but the meaning of the square root symbol is that it represents the square root function. The function can't give you but one thing out. You take the square root of 9, it gives you +3. Now, you might be working a problem where you're interested in -3. Well, then you didn't want the square root of 9, you wanted negative square root of 9. So there's these subtleties and maybe even shortcomings that come with dealing with functions. They're only going to give you one output. You got to know how to interpret that. This will already has played a role for us in terms of dealing with square roots, and maybe absolute values arise. We've done problems of that sort when we dealt with square roots. It becomes an even bigger problem when you deal with trig functions. You might take, or really when you deal with inverse trig functions, you might take an inverse sine or an inverse cosine or an inverse tangent of some input, and you're going to get a specific output, and you have to know how to interpret that. With square roots, you might have wanted the negative square root. There's only 2 choices. with these other trig functions, there's lots of choices. You have to know what's going on and what the calculator's doing. But we want to think of functions as machines. We'll have a little diagram here shortly. Speaking of the square root key in a calculator, it represents a function. You give it a number and it outputs a single value. But we can't take square roots of negatives, not in here. Let me emphasize, we don't take square roots of negatives. So the domain of the square root function is simply all non-negative real numbers. We can take square roots of all non-negative real numbers in set notation or in interval notation. Hey, what's the range? What can you get out of a square root function? Can you get 0 out? Yeah, put 0 in. The square root of 0 is 0. Can you get anything positive out? Yeah. Pick your favorite positive number, a, and you want to get a out of the square root function, put a squared into the square root function, and it'll give you a out, provided a is positive. If a is negative, then it's a different story. But in fact, the range is also 0 to infinity. Once we start graphing in the next section, you'll find that easier to visualize because we'll have pictures then. But the range of the square root function is also all non-negative numbers. Remember, you can only take square roots of negatives, and you never get negatives out of the square root function. You might be interested in negative things, but the square root function won't give them to you. It gives you positive square roots. A couple more. Number 34. Determine whether the equation y equals the absolute value of x defines y as a function of x. Okay, well, a function takes a good input that is something in the domain and gives you a single output. Does this do that? And by the way, what is the good input? What numbers, what real numbers, can you take the absolute value of? All of them. So by the way, the domain of this is all real numbers, or font for the real numbers, because we can take the absolute value of anything. Do you get a single output? Yeah, it outputs the absolute value of that input. So yeah, it only gives you one thing out. It's a function. Y is a function of x. Its domain is all real numbers. What's its range? What do you get out of this function? You don't get negatives out because absolute values are never negative. You can get 0 out, put 0 in. And you want any particular positive number out? You want to get positive number a out of this function? Then put a in. You could put negative a in. The absolute value would absorb that negative sign. There's actually two ways for you to get positive number a out of this function, by either inputting a itself or inputting the negative of a. And the range is non-negative real numbers, by the way. Finding domains is usually fairly easy, and we'll do it in this section. Finding ranges is harder. You kind of need a graph to find ranges. And at this stage of your career, graphing ain't your thing just yet. The reason finding ranges is hard is because it involves graphing, and graphing can be a bit of a challenge. Here's one that's a little more interesting because it's not a function. Determine whether the equation y equals plus or minus square root of 1 minus 2x defines y as a function of x. Again, for a function, you take any good input, that is an element in the domain, and it gives you a single output if it's a function, that is a single element of the range. Here, we can't let x be just any real number. We can only take square roots of non-negative things. So we need, they didn't ask us for the domain, but we need 1 minus 2x. We need that to be positive because we can't take square roots of negatives. So that would be an issue when we start looking at domains later. For example, if I take x equals 2, that generates plus or minus square root of negative 3. And in here, the square root of negative 3 is meaningless in here. There's people living perfectly happy lives with complex numbers. There's an appendix about that as well. but we're not covering that. It's optional material. It's extra material. There isn't time to do that and everything else. We're not dealing with complex numbers. So everything we discuss, except for some of the supplemental stuff, is about real numbers. So this doesn't work. But this doesn't really have anything to do with whether we're dealing with a function or not. I need to worry about putting one good number in and getting a single number out. It's the plus or minus that messes things up. That plus or minus square root thing is not a function. Plug in x equals 0. That's a good number. That's a number in the domain. That doesn't give us square roots and negatives. We can find the domain, but they didn't ask us to. If we plug in x equals 0, we get y equals plus or minus the square root of 1 minus 2 times 0. Plug 0 in right there. That's plus or minus the square root of 1. Square root of 1 is 1. So we get y equals plus or minus 1. So the input value of x equals 0, we get two output values, 1 and negative 1. That can't happen with a function. So this is not a function. This equation does not define a function. So the verbiage to use is, this is an equation. We could do some manipulation of this and turn it into a different equation, an equivalent equation. In fact, it would be something related to the graph of this would be related to a parabola. We'll touch on parabolas, I think, before the class is over. We'll do conic sections and precalculus too, in general. But we put one thing in, we got two things out, not a function. And those two things are produced by the plus or minus. That's really what caused the trouble. In a function, you put one good number in, a number in the domain, and you get one number out. And that number's in the range, by the way. Here we put a good number in, 0. We didn't get square roots and negatives. We did up here because we put a bad number in. That's not in the domain. But we put a good number in and we got two outputs. And that doesn't happen with a function. Back to the notes. Okay. We said, think of a function as a little machine. So here's a graphic of it. We often denote a function with a letter. If f is a function from set x to set y and x corresponds to y, we write, here's a notation I like, and no doubt you've seen before, we write y equals f of x. Read y equals f of x. So the machine idea is given in this figure 5 from the book. The idea is you input something from the domain. You put a good number in. X goes in here. F does some stuff to that number, and it outputs a unique number. That unique number is called y or f of x. Right, so we'll use these symbols interchangeably quite often. So input an x value into a function, a number from the domain of the function. You pick something outside of the domain, then the machine doesn't work. You put something that for which the function's undefined in. And we'll look at that in this section as well. But you input a good value and you get as output a single value. By the way, that single value lives in the range. Input an element of the domain, get out a single element in the range. Think of functions like that. You input something and it gives you a single output. Historically, exactly what a function is not a really old idea. Really, the idea of what a function is dates from probably around the year 1700, very ballpark. It's a relatively new idea considering how long math ideas have been around. Definition. We abbreviate the statement, f is a function from set x into set y as y equals f of x, where x is a variable element of set x called the independent variable, and y is a variable of set y called a dependent variable. It depends on x. Independent, dependent variables we'll use these a little bit. This terminology we probably won't see a lot of. We'll simply have X values and Y values, input values and output values, right? Right, thinking about the machine, input values and output values. That's how functions work. Let's do another one. Number 48, here's a function. Evaluate it at a bunch of places. F of X is the square root of the quantity X squared plus X. Find each of the following. F of 0, okay? We'll just, F of 0, we'll plug 0 in for X and see what that simplifies to. That'll give us 0 squared plus 0, square root of. 0 squared plus 0 is 0, square root of 0 is 0. There's the answer. I didn't put little boxes around these. I'm going to cram a bunch of them on a single slide. F of 1, do the same thing. Replace the X here and here with a 1. Okay. That'll give us 1 squared plus 1, square root of. 1 squared plus 1, 1 plus 1 is 2. That gives us a square root of 2. Can you simplify that? No. You could put it in a calculator and approximate it. Why approximate it? This is the correct answer. An approximation of that would not be correct. We'll keep precision as best we can. F of -1. Okay, wherever I see an X in the definition of the function, I always go back to the definition of the function. I'll replace the X with -1. So we'll get a -1 squared plus -1 square root of. Put parentheses around that stuff that was input, as I commonly do. -1 squared is +1 plus -1. That subtracts 1. 1 minus 1, 0. Square root of 0 is 0. Do we have a problem here? We had a 0 output up there. Can you repeat outputs? Yeah. You can't repeat inputs unless you get the same thing out. I mean, I can't plug 0 in up here and get out 0, and then down here plug 0 in again and get out 4. You plug 0 in, you only get one thing out. Now you can get the same thing out more than one time. When we plug in 0 and -1, both of those output 0, not a problem. It's a function. You put one thing in, you get one thing out. You might get the same thing out a couple of different times. Part D. So we're shifting from numbers in the next few to letters. What's F of -X? All right, people tend to mess this up, and it's not that complicated. You can do the same thing. Wherever you see an X in the definition of the function, you're going to replace it with a -X. Go back up here. X squared plus X, replace the X there with a -X, and replace the X there with a -X. I say it real quick. The idea being it's going to come in parentheses, and where the little hand's covering up stuff, that'll be replaced with -X. So we'll have -X squared plus -X. So we just did the same kind of thing using -1. Yeah, now we're using -X. What happens when you take -X squared? The negative disappears and you're left with X squared. Plus a -X is the same as subtracting X, but I don't think you can simplify that. There's no simplification that can be done here. There's F of -X. Part E asks you for negative F of X, a very different thing. We'll take the F of X function and put a negative in front of it. There's the negative, and there's the F of X function in terms of X. And that's the answer. I can't simplify it. That's it. So different things here. Here the negative was inside the function. Here it's outside the function. Well, I know what the function is. Just put a negative in front of it. There's the function. There's the negative. Part F asks you to find F of X plus 1. Right? Reading it fast again. F of X plus 1. Wherever you see an X up here in the definition of the function, there, there, and there, we're going to replace it with X plus 1. So F of X plus 1 would be X plus 1 squared plus X plus 1 square root of. X plus 1 squared plus X plus 1. Got the parentheses around it. The substitution has been made. Wherever there was an X here, we put an X plus 1 here. And then we'll take a square root. That is F of X plus 1. I guess for the record, how about we try to simplify that a little bit? It probably won't simplify a whole lot, but we can FOIL this out. It's a square. We'll have the first one squared plus twice the product plus the second one squared. Old news at this stage. That's x squared plus 2x plus 1. Over here, we've got an x plus 1. We can combine the x's and the 1s. We'll have x squared plus 3x plus 2. Right. So I can change it to that form if you're into simplifying. Part G, find f of 2x. Wherever I see an x in the definition, I'll replace it with a 2x. We'll get 2x squared plus 2x square root of. Done exactly that. Multiply out. 2x squared is 4x squared. Producing this, we got the 2x. Can't really do much with that. I'll leave it as given. Part H asks for f of x plus h. All right. F of x plus h. Wherever I see the x up here, I'll replace it with an x plus h. Just like we did with the x plus 1, except now we got an h. So more letters, less numbers. Doesn't matter, treat them the same way. So f of x plus h would be x plus h squared plus x plus h square root of. X plus h, quantity squared plus x plus h square root of. This looks just like that, except the 1's been replaced with an h. Yeah, this was x plus 1, and down here we got x plus h. Multiply out, similarly square, we can combine, and it looks like it simplifies down to something like this. How about, this is my own doings here, how about f of Bob? What does a function do to x? Squares it, adds x in, and then takes the square root. It doesn't matter what you put in for x, that's the manipulations. So what's f of Bob? Bob squared plus Bob square root of. No matter what you insert into the function treats it the same way. This is the recipe for the function. You substitute whatever you want in the function, you substitute all these x's over here with that thing. Don't make up any shortcuts. If you got a shortcut, it probably ain't right. If there was an easier way of dealing with this, we'd deal with it an easier way. In particular, with these plus 1's and plus h's. You don't just get a plus 1 off on the side or plus h off on the side. It's more complicated than that. Or actually, maybe it's easier than that. The pattern's always the same. You simply replace this, whatever the input is, in each of those x's over there. You want x plus h, put it there and there. You want 7 minus Bob, put 7 minus Bob in both of those places. That's what the function does to stuff. Simply substitute in, and there you go. Back to the notes. When a function f is defined by an equation in x and y, we say that the function f is given implicitly by the equation. What we'll do is we'll take that equation and solve it for y, and that will give the function implicit to the equation. I'm going to have to give you a warning about how this book treats that word implicit and how the calculus book treats it. It's subtly different. To see if y is a function of x, all we have to do is, like I said, solve for y. Solve the equation for y and see if we get an expression which will represent a single y value for each good input value of x, each x in the domain. It's a good value. I'll talk good and bad values, especially when we look for domains. A warning. So not all equations in x and y define a function. The ideas being discussed here are subtly different from the idea of what it means for a function to be implicit to an equation, as you'll discuss it in Calculus 1. The setting in Calculus 1 encompasses these things we'll do. I've got a hyperlink to some Calculus 1 notes there, so help yourself to that. But what we're doing here, we'll do it in the context that it's dealt with in this particular book. This context will mostly translate into the Calculus 1 context, but be warned, there's a little bit of difference. Consider the equation, x times y equals 4. Can you solve for y? Yeah. Y equals 4 over x. Divide both sides by x. So f of x equals, typoed there, 4 over x is the function implicit to this equation. Sorry, typo, we'll correct in the online notes. Should read 4 over x. We got y equals 4 over x, and we're making the substitution y equals f of x. Apologies for the typos. There are going to be a few of them left. How about the equation x squared plus y squared equals 1? Can you solve for y in this? Well, I could take the x squared to the other side and take a square root of both sides, giving us this. Maybe we deal with absolute values along the way, but we get y equals plus or minus the square root of 1 minus x squared. This equation is equivalent to that equation. But this doesn't define a function because of the plus or minus stuff. For example, plug in x equals 0. We'd have plus or minus the square root of 1 minus 0 squared. We'd have plus or minus the square root of 1, which is plus or minus 1. Can't get two values out when you put the one value 0 in, not a function. So in here, we would say this equation doesn't define a function implicit to that equation. We got this problem with the plus or minus stuff. Now here's some true observations. These comments, I don't think they're in the book. This is the kind of thing you'll see in Calculus 1. If we were to take y equals positive square root of 1 minus x squared, that is a function. And if you substitute that into this equation, you will get an identity. And that should be pretty plausible to you. If you take this equation, which is also defining a function, y equals negative square root of 1 minus x squared. Plug that in for y up here, you'll also get an identity. Substituting this for y or substituting for that for y, the positive square root or the negative square root, that substitution will make this equation true. In Calculus 1, you would say this function is a function implicit to this equation, as is the negative square root. Maybe g of x equals negative square root of 1 minus x squared. There's two functions that are implicit to the equation, and the use of the term implicit in Calculus 1. And here, we're using it differently. Here, we start with a given equation, solve for y in terms of x, and see if that's a function, which is different from what we just described in the last few sentences. So this is our angle on what it means to be implicit. Be warned, you'll deal with it in a different way in calculus. Subtly different, but different. So we'll solve for y when asked these questions about implicit to. We want to find domains. And this is where I'll go back to my good values and bad values. To find the domain of a function, we need to determine all the x values that are good values. Actually, how about we find all the bad values? They're usually easier to find. The easiest way to do this is to find the bad values and throw them out. So to find the domain of a function, we'll see what can go wrong. Take this with you in your future mathematical travels. It'll work in Precalculus 1, it'll work in Precalculus 2, it'll work in calculus. Find bad values and throw them out. What makes it bad? Where we stand now, the forbidden operations are division by 0, and this will remain a forbidden operation throughout your future mathematical travels, and square roots and negatives. This will remain a restriction if you restrict yourselves only to real numbers. If you go to complex numbers, this will change. But for us, no division by 0, no square roots and negatives. Anything else? Yeah, later on, you're going to learn some more functions. You'll learn a logarithm function. You can't take logarithms of negatives. You can't take the logarithm of 0. Inverse trig functions, say inverse sine. You can't take the inverse sine of numbers greater than 1 or less than -1, unless you want to use complex numbers. But at this stage, all we have to worry about is division by 0 and square roots and negatives. There's stuff that lies ahead of you. This in Precalculus 1, trig functions in Precalculus 2. So some things go wrong, but at this stage, these are the only two things that can go wrong because these are the only kinds of formulas and equations that we'll consider. So with that idea of finding bad things and throwing them out, let's look at number 58. Find the domain of this rational function, ratio of polynomials, g of x equals x plus 4 over x cubed minus 4x. Express the answer in interval notation. Okay, as we just said, only thing that can go wrong is division by 0 and square roots and negatives. How do you feel about this? There's no square roots, so square roots and negatives isn't a problem, but there is division. There is division, so we can't have division by 0. So let's see when that happens. Let's factor the denominator. We've got, here it is, x plus 4 in the numerator, no factoring of that. It's already so-called a linear term. In the denominator, we've got x cubed minus 4x. Well, we can factor an x out for sure. Ooh, x can't be 0, or we have division by 0. I see that from here. X squared minus 4, difference of two perfect squares, factors into x minus 2 times x plus 2. These things are dealt with in the appendices. It follows from FOIL, first, outer, inner, last. So we get this kind of factoring. And now I can see exactly where the problems are. The problems are when this denominator is 0. So x is in the domain of g unless x is a bad value. A bad value makes the denominator 0. So let's find where that occurs and throw those out. If we have x times x minus 2 times x plus 2 equals 0, then either this equals 0, x equals 0, this equals 0, x equals positive 2, or this equals 0, and x equals negative 2. Solving each of those expressions, set equal to 0, this was called a zero product property, I think it was, in some of the appendices. But factor, set each factor equal to 0, that'll tell you where that expression is 0, and that's where the problems are. So these are the bad values. All right, we weren't looking for the bad values, strictly speaking, we were looking for the good values, where everything's good except for these three, because the only thing that could go wrong is division by 0, and that happens here. So the domain of G is all real numbers except for, let's list them in order, -2, then 0, then 2, listing them lesser to greater. So in interval notation, we'll have the whole real line. Interval notation is discussed in the appendices as well. The whole real line from -infinity to infinity, but we'll remove -2 and 0 and 2. So we take that interval from -infinity to infinity and remove -2 and remove 0 and 2. Pop out those three numbers. Remember, we use the parentheses to indicate open intervals. Again, if this is a problem, look at the review sections on intervals and the videos posted that cover those sections. But this is how we'll go through and remove -2. This includes all numbers strictly less than -2. This includes numbers strictly between -2 and 0. By strictly, I mean, as explained in the appendices, excluding the endpoints. These are all x's between 0 and 2, excluding 0 and 2. And this is all x strictly greater than 2. So all we've done is removed 2 and 0 and -2. In interval notation, there's the domain of that function. Let's do another one. Find the domain of this g of x, square root of 1 minus x. Okay, the only thing that can go wrong is division by 0 and square roots and negatives. This time there's no division, but there's square roots. So we need the expression under the square root radical to be non-negative. We can't take square roots of negatives. That's a bad thing. So we're finding bad values. We'll throw those out. That is, we need 1 minus x to be greater than or equal to 0. We need this to be greater than or equal to 0. I guess we're actually finding good values in this one. Find the bad values, negate this inequality. But let's take a positive perspective on this one. That's got to be positive. I'm sorry, non-negative. So 1 minus x is greater than or equal to 0. Those are the good values. That is, 1 is greater than or equal to x. Take the x to the other side if you like. Written in the reverse order, x is less than or equal to 1. That's the domain of G. They wanted this one in interval notation as well. Fine. Then the domain is anything less than or equal to 1. A 1, a square bracket. Remember, the square bracket means it includes 1. 1 is in the domain, right? Right. You plug 1 in, you'll get 1 minus 1, square root of, that's the square root of 0, and the square root of 0 is 0. You can't take square roots of negatives, but you can take the square roots of positives, and you can take the square root of 0 as well. So we get this for the domain of that function. The constraint came from the presence of the square root. Back to the notes. They introduced something called a difference quotient. Rather uninspired, but in the first half of Calculus 1, you'll deal with difference quotients. They lead into things called derivatives of functions. But for us, it's just something to compute using a function. Of course, we're doing this because this is pre-calculus, but the difference quotient of function f at x is given by f of x plus h minus f of x quantity divided by h for h not equal to 0. Of course, h can't be 0. It's in the denominator. Some examples. Find the difference quotient, f of x plus h minus f of x quantity divided by h, where h is non-zero, and simplify it for f of x equals negative 3x plus 1. All right. A couple of examples ago, we dealt with this f of x plus h kind of stuff. You simply go to the definition of the function f. Wherever you see an x, replace it with an x plus h. So for f of x plus h, we'll have negative 3 times x plus h plus 1. Negative 3 times x plus h plus 1. Replace the x with the input, x plus h. Got parentheses around that. There's the f of x plus h part. Subtract f of x. Okay, well, that's just negative 3x plus 1, so subtract that. Be careful. You're subtracting. Don't forget the parentheses. We'll have to deal with some distribution here. Since this is the function, that's what f of x plus h is. Of course, that's what f of x is. Don't forget the parentheses because you're doing some subtraction here. And we got the h in the denominator. How about we distribute? They told us to simplify. Negative 3x minus 3h plus 1 minus a negative 3x is plus 3x. Because it's a minus 1 here. So simplifying somewhat. And then some stuff cancels in the numerator. Negative 3x plus 3x. Those cancel out. 1 minus 1 is gone. You're just left with a negative 3h in the numerator and an h in the denominator. Simplifying. Can you cancel those h's? Be careful with this stuff. We went through this in great detail in the appendix on rational expressions. No, you can't just cancel those h's unless you got more information. Notice h can't be 0 here. Can h be 0 here if I just look at this little piece? Yeah, I plug in h equals 0, I get out negative 3. Plug h equals 0 in here, I get in trouble because I can't divide by 0. So negative 3h divided by h does not equal negative 3. Because I can plug h equals 0 into this and not into that. They don't even have, as functions of h, they don't even have the same domain. So I need to add to this, don't plug in 0. So we'll do that by saying they're equal. Negative 3h over h is equal if h is not 0, or in this case, they gave us that since h is not 0. So the difference quotient, where h is not 0, is negative 3. I can't emphasize this little extra piece of information enough. In Calculus 1, you're gonna wanna make h really close to 0. You'll be taking a limit as h approaches 0 in this process. And that's a super subtle idea, but it requires that h not be 0. So h is not 0, that justifies the cancellation. And I will repeatedly make a big deal out of that. It's so central to the ideas in Calculus 1. And these simply are not equal to each other without that little extra knowledge or that little extra statement. Let's do number 90. Difference quotient. You're told h is not 0. And simplify for f of x equals the square root of x plus 1. Okay, same idea. These kind of work themselves to a degree. You just substitute in. Then you simplify. And the simplification in this one's a bit trickier. That's why I chose to do this one. F of x plus h minus f of x over h. F of x plus h, I just go up here to f of x and replace x with x plus h right there. So we'll have x plus h plus 1, square root of. Substituting in, there's the f of x plus h. Subtract f of x, there's f of x. We'll put that there. Divide by h. We've evaluated the function. Like I said, this one's a trick, and that's the reason I wanted to do it. How about this? Let's multiply by 1, but a very special version of 1. We've seen things like this when we rationalize the denominator in the appendices. Here we're going to rationalize the numerator. I got my reasons. So I'd request you just sit tight for a second on this one. You should be able to follow the computations, but the motivation of doing this is not very clear. This is the common way to deal with these kinds of things in Calculus 1. For now, see if you just believe and can follow the computations. Let's multiply by this thing here divided by itself. So this is just 1. We just multiply by 1. Why? Here's why. Hey, look at this. When we multiply the numerator by this, notice the form of it. We've got thing 1 minus thing 2 times thing 1 plus thing 2. Well, when there's something of that format, you're going to get the first one squared minus the second one squared, FOIL it out, the center terms cancel. So this will produce, you might want to pause the video and convince yourself of this. We get the first one squared minus the second one squared. That's the reason we multiplied by this form of 1. That gets rid of the square roots in the numerator. So the square roots are gone. We've got the square root squared. That just produces the quantity, x plus h plus 1. Square root squared. That just produces x plus 1. I've been insistent that you treat square roots and squares with the appropriate respect. Sometimes you get absolute values. This isn't that time. You get absolute values when you take a square root of something squared. Here we're taking the square of a square root. Let me run those words by you again. When you take the square root of something squared, you get the absolute value of the something. When you square a square root, you simply get the stuff inside the square root. Order matters. Here, no absolute values. We're squaring, we just get the stuff inside the square root. That's why we did this, to simplify the numerator. All right, so let's do some more stuff. This is so we can further simplify the numerator now that we got rid of those square roots. Okay, we introduced some square roots in the denominator, agreed. We made the denominator messier, but some good things are going to happen. Just make sure you can follow the computations. The motivation, I agree, is foggy at best. So let's see, here's where we left off on the previous slide. Here's an x minus x, and here's a 1 minus 1. When we distribute, those will cancel, and we'll just be left with the h in the numerator. Just an h in the numerator. Can you cancel those h's? As long as h is not 0, you were told h is not 0, but definitely include that information. We get the cancellation provided h is non-zero. So the difference quotient simplifies down to this thing. And I don't think you can really make that any simpler. We could rationalize the denominator. We'd just be going backwards if we did that. We get back upstairs to where we similar to where we started. So this is the intended solution. Again, don't forget h is not 0. That one's pretty tricky. You should be able to follow those computations more than anything instead of thinking of the trick. But the trick was to multiply by something appropriate to get rid of the square roots. And once we did that, things simplified and we were able to do some cancellation. You will see problems like this in Calculus 1. Okay, one last glance at the notes. We can perform the following operations on two functions f and g. So we're going to be given functions f and g, and we're going to make a new function using those two old functions. We can define the sum f plus g of x. All right, so we're defining a new function of x, a function denoted f plus g. F plus g of x is defined to be, it's a definition, f of x plus g of x. F minus g as a function of x is defined to be f of x minus g of x. F times g as a new function is defined to be f of x times g of x. F divided by g is defined to be f divided by g of x equals f of x over g of x. Oh yeah, don't divide by 0. So all we're doing is taking sums, differences, products, and quotients of existing functions and producing a new function. Let's look at some final 3 exercises to illustrate that. Suppose f of x is the square root of x plus 1 and g of x is 2 over x. Find the formula for and the domain in interval notation, okay, of f plus g of x, f minus g of x, f times g of x, and f divided by g of x. Part A, they want the sum. F plus g of x by definition is f of x plus g of x. Now substitute, we use the definition to justify this equality. You know what f and g are, they were given. So we substituted in square root of x plus 1 for f, 2 over x for g. We've substituted in. There's the sum of those two functions. Let me do a little more algebra. Let's get a common denominator and add them together because I want to. You might have to do this to get the answer in the book. We were asked more than just for the function. We were also asked for the domain. So we'll need this in a second. So let's multiply by x over x. That'll give us the common denominator here, and we'll have x times square root of x plus 1 plus 2, both divided by x. We had the common denominator, introduced an x, we'll write out front. So there's, as a rational expression, there's the function f plus g. Okay, they want the domain. All right, well, let's find bad things. Bad things are division by 0 and square roots and negatives. We've got some division, there's a denominator. That's why I wanted to combine these two. Denominator of x, well, x can't be 0 because we can't divide by 0. So the division by 0 constraint tells us x is not 0. Any other constraints? Yeah, you're also taking square roots. It involves the square root of x plus 1. Well, then x plus 1 must be greater than or equal to 0, must be non-negative. So we'll take x plus 1 is greater than or equal to 0. That is, x is greater than or equal to -1, subtract 1 from both sides. So we need both of these to occur. X greater than or equal to -1. With that alone, in interval notation, is x is the interval from -1 to infinity, just this part here. Again, we have an appendix on interval notation without getting into all the details on that here. You've got a reference elsewhere. X greater than or equal to -1, square bracket, -1 to infinity, so to speak. Oh, and x can't be 0. So kind of similar to that last one. That second condition says remove 0. So open parentheses on both sides. This is everything greater than or equal to -1 except for 0. We removed it. It's a little, remove it, pop it out. And there's a domain in interval notation. Let's look at f minus g of x. Well, it's going to be the same thing. Basically, we'll have a negative there, 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 and there. We'll have the same problems. We'll have the same division by zero concern, and we'll have the same square root of negative concern. So part B, f minus g of x, take the difference, substitute in, get a common denominator. Same thing we just did, except now there's a negative sign there. It cascaded through the computation from here. As before, what's your problem? Square roots of negatives, producing this condition, and division by zero, producing this condition. These are the same conditions we had previously, and we get the same domain as before. Let's do another one. Part C says deal with the product. Okay, I think the answer to the next ones is the same thing as well, possibly all of them. F times G. Okay, this time it's a product. F of x times g of x. F of x is the square root. G of x is this 2 over x thing. So, well, rewrite it a little bit as given here, and you got the same problems. Division by zero, x can't be zero. Square roots and negatives are forbidden, implying x is greater than or equal to -1 as before. These are the same two conditions we had before, same domain as we had before. Okay, let's look at the quotient. This is going to look a little weird, but we'll be very careful in the manipulations. F divided by g of x. That's f of x divided by g of x. That's the square root of x plus 1 divided by 2 over x. Okay. There's the quotient. I want to write it in a different form. Can x be 0? No, because you got divided by x right there. And we can't divide by 0. X can't be 0. I want to rewrite this, eliminate the compound fraction by saying, hey, dividing by this parameter in the denominator is the same as multiplying it by it in the numerator. We're doing a multiplication by the reciprocal thing is how to interpret division. So 2 divided by x in the denominator is the same as x over 2, right? It's a reciprocal of this. The reciprocal of 2 over x is x over 2. So I can move that x to the numerator. Can x be 0 here? If I just concentrate on that little expression there, sure, I plug 0 in, we get 0 times the square root of 1 over 2. We get 0 out if we plug 0 in. But I just said you can't plug 0 in. You can't plug 0 in from the division here. This expression and this expression are not equivalent. They differ. The only place they differ is at 0. Well, you better write that out then. Can you plug in 0 here? No, because of the division by 0. Can you plug in 0 just in this little expression here? Yeah, nothing goes wrong. But if I say this equals that, I got to eliminate the fact that you can't have 0 for the x value. That's information contained here that if I keep just that, disappears. So I got to write it out by hand. Again, see the appendix on rational expressions, and this is dealt with at some length in the examples in that section. So I have to write this in by hand. X doesn't equal 0. Either that or leave it in this form. This is simpler, but it comes with this little caveat to this condition. X is non-zero. Okay, looking at this, what can go wrong? Division by 0. Well, there is no division here, though it's what produced this little extra condition on the side. And square roots and negatives. So again, we need x plus 1 to be non-negative. That leads to the condition x is greater than or equal to -1. Along with that, we have the condition that x equals 0 is not in the domain, so x is non-zero. Cascades through as well. And these are the same two conditions we had before. I've worded it slightly differently in this one. But we have this condition combined with the fact that x is non-zero. And that's the same thing we had before, and it's the same domain, same interval notation. That's a coincidence. These 4 functions produced exactly the same domains. Yeah, probably a little bit. I'm sure I could find F and G where that's not the case. where the sums and the quotients and so forth, some of those have different domains, especially this quotient thing. We could probably tweak that and find something a little bit different. So it somewhat is a coincidence that each of those led to the same domain. Let's do an applied problem, a word problem. Story is, if a rock falls from a height of 20 meters on the planet Jupiter, its height h in meters after x seconds is approximately h of x equals 20 minus 13x squared. Part A, what's the height of the rock when x equals 1 second, when x equals 1.1 seconds, when x equals 1.2 seconds? So we'll have some messy numbers will come out of these decimals. When is the height of the rock 15 meters? When is it 10 meters? When is it 5 meters? Part B. Part C, when does the rock strike the ground? All right, not pertinent to our agenda here, but hey, Jupiter's a gas giant. It doesn't even have a ground. It's denser and denser clouds as you descend into Jupiter, overlooking that little astronomy boo-boo. They're really just asking us when is the height 0 measured from some level, assuming this function for height. All right, so part A, we've got a function for height. There it is. When x is measured in seconds, right, we'll plug in x equals 1. When x equals 1 second, the height is h of 1, 20 minus 13 times 1 squared. Plug in 1 for x right there. That's what, 7? And the height was expressed in terms of meters, they said. So 7 meters. Maybe arguably should include the meters as part of the answer. In a physics or engineering class, they'd be big on the units, appropriately so. The answer really is 7 meters, more than it is just 7. When x equals 1.1 seconds, we'll plug 1.1 into h, and that'll give us 20 minus 13 times 1.1 squared. I leave it to the calculator to do the messy arithmetic. We find that's 4.27 meters. Plug in 1.2 seconds. At 1.2 seconds, plug in 1.2 for x, produces this, which simplifies down to 1.28 meters. Does this make any sense? The story was, a rock falls from a height of 20 meters. You might imagine they've released the rock and it's descending. As time goes by, its height decreases. It starts at 20 meters, 1 second later, it's at 7 meters, another tenth of a second later, it's at 4.27 meters. It's getting lower than 1.28 meters, another tenth of a second. So the rock's descending. The fact that these numbers are decreasing makes sense. It's falling. Part B, got that restated. Yeah, part B, when is the height of the rock 15 meters? When is the height 10 meters? And when is the height 5 meters? Well, the height is given by this function. So we want to set the height equal to 15 meters and solve for the time. So we'll set h of x, 20 minus 13x squared, set that equal to 15 and solve for x. So rearrange, subtract 20 from both sides. That'll produce a -5 on the right-hand side. Let's get the -13 out of the way. So we'll get x squared is -5 divided by -13. Get those two negatives cancel. We get x squared equals 5 over 13. Or x itself is taking a square root and respecting the absolute value that is introduced. Here we take a square root of a square. That's when you need the absolute value. And that's where the plus or minus comes from. So we get x is plus or minus 5 over 13, square root of. Presumably the time is always positive. I mean, they didn't say that. This x value of negative square root of 5/13. I mean, that also solves the equation. It depends on the physics problem. They didn't describe it in great detail. They said it falls from a height 20 meters. Yeah, did you hold it 20 meters off the ground and release it? Equivalently, you could have thrown it up in the air and it went up to 20 meters and then started to descend. And we get the same kind of formula is given here. And when time equals 0 would be when it reaches its maximum of 20 meters and starts to come down. Physically, that's the reason we're getting two solutions, when the rock was going up and then when it was coming back down. And that'll happen in all three of these in part B. If we assume they want the time to be positive, then it's x equals positive square root of 5/13. There it is. It's a decimal approximation from a calculator. When the height's 10 meters, we'll set that function equal to 10. Do similar manipulations that will produce plus or minus 10 over 13, square root of. Presumably they want the positive time, positive square root of 10/13. That's about 0.877 seconds, right? They're giving us lesser heights. It takes it longer to fall to that height. So the times are going up. I mean, that should make physical sense to you. When the height's 5 meters, we'll set the function equal to 5. Similar solving, we'll get plus or minus 15/3 square root of 1.074 seconds approximately. And that makes sense. The height's decreasing as the time increases. You've dropped it and it's decreasing. So. Part C, when does the rock strike the ground? A useful hint for you in this class and many future classes, be they calculus, physics, engineering, when there's dynamics problems. When? What do they mean by when? They mean what's the time value? And for us, X measures time in seconds. So when they say when, in this problem, it's X equals what? When the rock strikes the ground. You know, that thing about there not being a ground on Jupiter, we'll overlook that. They want to know when the height's 0. So we'll set the height equal to 0 and solve for X, time. That's when. We'll have this equation initially, take the 20 to the other side, divide by the 13, that produces X squared is 20 over 13. Take a square root, you get the plus or minus, presumably time is positive, and we'll get 1.240 seconds. So there's a solving, again, for time given height. And we got lots of square roots to pop up because of that X squared there. We were solving for X, so at some stage we had to take square roots. And we got the plus or minus stuff as legitimate solutions. If this were a test question, I'd say both of these are fine answers. And finally, something a little bit different, just threw this one in. It deals with more business and economics ideas. So suppose that the revenue R in dollars from selling X clocks is R of X equals 30X. The cost C in dollars of selling X clocks is C of X equals 0.1 X squared plus 7X plus 400. So you make and sell X clocks. This is the money you make by selling them. You incur cost when you make X clocks, keeping the factory open. Sometimes it's called fixed cost. If you plug 0 in, you get this, paying for the electric bill and so forth, rent. But there's materials and shipping and so forth. There's all the costs associated with producing X clocks. So the profit function is the amount of money you bring in minus the amount of money you spend. So profit is revenue minus cost. They're telling you that here. They've given you R of X and C of X. They want you to find P of X. Part B, find the profit, P, when X equals 30, and then interpret P of 30. Part A, profit is P of X equals R of X minus C of X. Okay, R of X is 30X, right there. C of X is this quantity here, right there. Take the difference. We'll get the negative 0.1 X squared. There's 30X minus 7X produces a 23X, and distribute the negative to get a minus 400. There's the profit function. Part B, find the profit if X equals 30 clocks are sold. We'll just plug 30 in. We get P of 30. That would be, let's see, look over here, that'd be negative 0.01 X squared, negative 0.01 30 squared, plus 23 times 30, 23 times 30 minus 400. crunch those numbers, calculator, the 30 squared and the tenths, and you'll get $200 from that. So there's the profit on selling 30 clocks. They ask you to interpret P of 30. It's the profit on selling 30 clocks. If 30 clocks are made and sold, then the profit's $200. And that's it for section. So we'll go back to the notes. And that's it for this section on introducing functions. We've seen profit functions, height functions, square root functions. It popped up. What we'll look at in the next section is graphing functions. So we really didn't do any of that here. We had those funny little pictures where we had sets. That's largely behind us, mapping Bob to Marcia and Diane or whatever it was. We'll deal more with algebraic functions, the f of x kind of functions. We're not done finding domains. We'll find ranges at some point, but finding ranges is really tricky. Finding domains, not so much. But we'll deal with the results of graphing some elementary functions in the next section. And throughout this chapter, we'll look at a good deal at graphing functions. So I'll see you in section 2.2 shortly, and we'll consider graphs of functions. Have a nice day.